Hello and welcome to lecture 10, part 2. In the previous lecture, we looked at the grand composite curve and we showed that how we could construct a grand composite curve from a problem table information and also from composite curves once they have been shifted in temperature. For example, hot composite curve down by half a delta T mean and cold composite curve by up by half a delta T mean. In this section, we will look at how we can use the grand composite curve information and determine which utilities we should use to satisfy the heating and cooling requirements and how we can target the amount of hot and cold utilities if we, for example, if we are using multiple types of utilities to satisfy the heating and cooling requirements. So let's start off by looking at this example here. So here we have the grand composite curve that is shown by this graph here. And then here we have a pocket that is the process to process heat transfer. And for this example, we have decided that the total amount of QC min, that is the hot utility requirement of the process, is to be satisfied by using high pressure steam. Okay. So we are providing the high pressure steam to satisfy the heating requirement of all these process streams. And this high pressure steam is quite expensive. So is there any other alternative? So yes, there is an alternative. So we can use a mixture of different pressure steam. So for example, for this part of grand composite curve, we can use high pressure steam. Then for the case of this part of the grand composite curve, we can use the medium pressure steam, and then for the last bit here, we can use the low pressure steam. So by using or by replacing high pressure steam with low pressure steams, we can actually make the process more beneficial because cost-wise, because high pressure steam is very expensive compared to low pressure steams. Okay, so in case of steams, as the pressure increases, the cost of generation of that pressure steam also increases significantly. Okay, so by replacing a high pressure utility with low pressure or low value utilities, we can actually make this process more economical. Okay. Another thing to notice on this grand composite curve, that this high pressure steam here is actually not shown at its actual temperature. So it is shown again at a shifted temperature, and it is down by half delta T min. And it means that the actual temperature of the steam is half delta T min, what is shown on this grand composite curve. Okay, so this is important for the next slide. So we have this grand composite curve, and we are supplying different utilities to satisfy the heating requirement of this process. And we notice here that the point where this MP steam or this LP steam is touching the grand composite curve, the delta T min seems to be 0. Okay, so it means that there is no heat transfer between MP steam and the cold utilities that need that heat. But in reality, as I said on the previous slide, that this temperature is not the actual temperature. Okay, so the hot utility is shown by half a delta T min down than its actual temperature, while the cold stream is shown here by half a delta T min above its actual temperature. So in reality, even if when they are touching, there is still 1 delta T temperature difference between the medium pressure steam and the cold stream that is taking the heat. And similarly for the case of LP steam. So by that definition, similar to a pinch temperature, we can define these points as utility pinches. Okay, because in a normal pinch temperature or normal pinch point, you have the difference between hot composite curve and the cold composite curve is 1 delta T. And by the same definition, here we have 1 delta T between the hot utility and the cold utility. And by that definition, we can call them as utility pinches. Okay. Now, these utility pinches are going to be very important, and we will see in the next slide how we can actually use these utility pinches in design. Okay. but this is just to say that where this utility touches the grand composite curve is what we call a utility pinch. So okay, so we have another example here, and here we for example have a hot oil circuit, and a hot oil circuit is where, for example, we are providing the heating requirement of the process by using hot utility instead of the steam. And here, for example, we have the hot oil that is at a temperature of T supply, okay, and it heats up and it goes to the process, delivers the heat, and then returns back to the furnace to reheat at a return temperature, and then the circuit continues, okay. And we have obviously a pump here that we need for the circulation of the hot oil, and we need to provide power to this pump. So if we try to represent this process here, that is shown as a process on the temperature enthalpy diagram, so we can see that we have T supply, that is the supply temperature of the hot oil, and then we have the return temperature, and this return temperature is actually comes as a output of the mass flow rate. So what mass flow rate we are using here, so that defines what temperature of the return of oil we will have. And then we have the process stream that is going from T supply to T target, and as such it's taking the heat from the hot utility. Okay, in terms of the hot oil circuit, the total cost of this process consists of two types of cost. One is the capital cost, and the second one is the energy cost. And in terms of the capital cost, we can consider the furnace, pump, pipe, and all the equipment that we have to purchase to develop this oil circuit. For the case of energy cost, we have the pumping, because we have to provide the power to the pump, so that is the energy cost. And then we have the fuel itself, because we have to supply fuel to the furnace. And depending on the efficiency of the furnace, we define what is the quantity of oil that we need to provide. So if the furnace is highly efficient, we need to provide less oil, but if the furnace is kind of poor in efficiency, we have to provide large quantities of oil. So in terms of the supply and the return temperature of the oil, that is for example a big design decision. So for example, what temperature of the oil to use and what its return temperature should be. The supply temperature mostly comes from the design of the process itself, okay. So the higher the supply temperature, the better. For example, the less oil we have to use, and similarly the return temperature also affect the mass flow rate of the oil. And normally we optimize this return temperature based on the process optimization, okay. So what will be the return temperature comes from the optimization process rather than just we select a temperature, okay. And when we are making these decisions about the supply temperature or the return temperature of the oil, the grand composite curve provides us the information that help us make those decisions. So that's one of the uses of grand composite curves, is to actually provide this information so that we can make appropriate decisions about the flow rate of the oil, or the temperature, supply temperature and return temperature of the oil. And we will see in the next slide. So here we have a grand composite curve that is shown with this dark line here. And then we are providing hot oil as a utility to satisfy the heating requirement of this process. And the hot oil is at 300 degrees centigrade, or is supplied at 300 degrees centigrade. But the temperature that is shown here on the grand composite curve is actually 290 degrees centigrade, because this is half a delta T min lower than the supply temperature. So 300 degrees centigrade minus half a delta T min of 20, that is 10. So that will be 290 degrees centigrade. And then we have these lines here, and these lines actually show the mass flow rate of the oil. So if you remember, the delta H is equal to capital Cp min, so that is the m dot Cp, that is the specific heat, and this is actually the flow rate temperature of your oil. So the slope of this line dictates the mass flow rate of the oil. So if you have a higher temperature here, it means that you have more oil mass flow rate, and if you have a lower temperature here, it means that you have less mass flow rate. So ideally speaking, we always want to, or optimally speaking, we always want our return temperature of our oil to be the pinch temperature of the process. Okay, so for example, the pinch temperature is here 200 and 120 degrees centigrade. So ideally, if it is possible, we want our return temperature of the oil to be same as the pinch temperature of the process. And if the pinch is 120 degrees centigrade, the actual return temperature of oil would be 130 degrees centigrade. That is actually half a delta T min above the pinch temperature of 120 degrees centigrade. Okay. Yeah. So if we want to increase the return temperature of the oil, it means that for the same amount of heat provided, we need to increase the mass flow rate of the oil. And as I said, that is represented by Cp min. So when the return temperature increases, this Cp min increases, and it means that there is now we have to supply much more oil to the process. So ideally, as I said, we always want the oil, the return temperature to be at the pinch temperature, but unfortunately, it is not always possible. And let's we can see on the next slide that what are the scenarios when it is not possible. So here, for example, we have another different shape of Grant composite curve. We have the same supply temperature of 300 degrees centigrade, and that is shown on the Grant composite curve by 290 degrees centigrade. And now if we try to use this 300 degrees centigrade and then go to the pinch temperature, we can see that we have to go or cross the Grant composite curve. Okay, and that is not possible. It means that we cannot cross the Grant composite curve. Sorry. So in this case, we have to go with the next best case, and that is by actually going to from this point, that is the supply temperature, and then touching the Grant composite curve to a temperature that is somewhere here, the return temperature that is above 120 degrees centigrade. Okay, so that is the next best case scenario. And because we cannot actually cross the Grant composite, because that will not be allowed in the process. So ideally, we want the return temperature to be 120, but it would not be possible. So we have to go to this temperature. And again, if we want a higher return temperature, it means that we have to increase the mass flow rate of the oil. And by increasing the mass flow rate of the oil, we have to provide extra pumping to the process. We have to provide more oil to the process. So that is not optimum in any case. Okay, so if we cannot go and get get a return temperature of the oil as the pinch temperature, then we have to use the next best guess, that is touching the Grant composite curve and then using the temperature that is here, for example. Now the next question is that how do we place the utilities, and how many utilities we supply for our chemical process. So we could supply a large number of steam levels, for example, based on the fact that each steam level here is slightly lower cost at our, for example, compared to the higher level here. So here you have the highest cost, and here you have the lower cost utilities. However, each level or each of these utilities add a cost complexity in terms of the number of steam mains that has to be supplied to the steam at these different levels. Okay, so because you have to supply this steam from different steam levels or steam, for example, lines, so it adds a lot of complexity, a lot of equipment requirements, a lot of piping to supply these utilities. Okay. So the saving in terms of the cost have to be, for example, offset against any additional capital cost in supplying that utility at all these different levels or pressures or temperatures. Okay, So we have to be careful in terms of how many different types of utilities that we can use. But at the same time, we have to make sure that it is not kind of adding so much complexity to the overall design to offset the balance that or the advantage that you are getting by using these extra utilities. Okay. Uh, we have also got the possibility of using any excess heat below the pinch temperature to generate steam. For example, here, so generally speaking, we could use the cooling water to deposit or reject all this excess heat, or it may be that it is required by the process. But if we have a choice, so we can look at the temperature axis. So for example, here we can see that the pinch occurs at quite high temperature, that is 180 degrees centigrade. So we have quite a huge delta T available, and it will be a loss of opportunity if we actually dispose of all of this heat to the cooling water. So instead, we can use this available delta T or available heat to generate low pressure steam. Okay, so we can use the temperature that or the heat that is provided by this process steam here, and then use the steam or actually so here obviously we just have shown the latent heat, but actually it also means the heating of the boiler fluid and also generating the steam and possibly superheating as well. But here we just have shown the latent heat as a simplified version of it, just to show that how much, for example, heat can be removed from the process and can be used to generate steam. Okay. So below this temperature of, let's say, around 120 degrees centigrade, so we can use the remaining heat because we are not going to, or like for example here, up to this point, we have a temperature of 70, 80 degrees centigrade. So we are not going to produce heat, steam by this temperature here. So we can use this remaining process heat to the cooling water. Okay. So instead of wasting all this heat here to the cooling water and using cooling water as a utility, we actually use some part of this process heat to generate steam that can be used in another part of the process. And then the remaining heat, we are actually disposing it to the cooling water. And the sum of the heat duty of the generating for steam and the heat that is given to the water, the sum of these two gives us the minimum QC min of the process. So here we could have actually a more realistic graphical representation for the production of our steam or generation of our steam from the process heat. So for example, we can show here that we have the steam profile. So we have the boiling feed water that is heating to its boiling point, and then we are using the steam generation, the latent heat of steam generation, and then possibly some superheating as well. So we can show this steam profile against the grand composite curve with the heat being used to generate or produce that steam, for example. So from its initial temperature to its superheat temperature, and in a more far more realistic representation than just showing the latent heat like we saw in the previous slide. Okay. And again, below this point here, for example, the excess heat that we can actually just dispose of to the cooling water. So you can clearly see that from this point to this point, all the heat, the excess heat, is actually goes to the cooling water as the cold utility. Okay. So that's all for this part. And in the next part, we will look at some other possible situations where we can use a mixture of different utilities.